Hello everyone, and welcome to part 2 of nucleophilic substitution reactions. In this video, we will be covering nucleophilic substitution mechanisms, which are a requirement for IB higher level chemistry students. Generally speaking, there are two main mechanisms for nucleophilic substitution: SN1, listed over here, and SN2. I will summarize, as you can see here, the points that will be discussed for both mechanisms are listed below, which we will be covering throughout the series of videos to follow. There are two main types of nucleophilic substitution mechanisms. There's SN1 mechanisms and SN2 mechanisms. You might be asked in exams to state the meaning of SN1 and SN2. It might be obvious in terms of the letters. S stands for this reaction being a substitution reaction, and the species substituting another atom in a molecule would be a nucleophile, as stated in part 1. As for the number, SN1, 1 stands for the molecularity of the rate determining step, which was covered in topic 16, 6 and 16 of the IB syllabus. Generally speaking, the molecularity of the rate determining step refers to the number of molecules reacting in the rate determining step. Thus, the maximum number of particles reacting in any one step in a mechanism is 2. Thus, you could have a unimolecular rate determining step, such as in SN1, or a bimolecular rate determining step. A unimolecular rate determining step means one molecule is reacting in the slow rate determining step of the mechanism. For example, a molecule could break into two different molecules. On the other hand, SN2, bimolecular, refers to two molecules reacting in the rate determining step. For nucleophilic substitution reactions, we only have two molecules reacting, which is the halogenoalkane reacting with the nucleophile. Thus, if it's a unimolecular rate determining step, this means the mechanism must be a two-step mechanism in which an intermediate is formed in the first slow rate determining step, which reacts in the second part of the mechanism. While in a bimolecular rate determining step, since we only have two reactors, this means the mechanism is a one-step mechanism, since both particles, the halogenoalkane and the nucleophile, are reacting in the same step. SN1 type mechanism dominate in tertiary halogenoalkanes, while SN2 mechanisms dominate in primary halogenoalkanes. I've placed a note here in the side to state that secondary halogenoalkanes undergo both SN1 and SN2 mechanisms equally. The reason behind this will be discussed in part 3 and 4. An SN1 mechanism requires the formation of an intermediate, as stated when I explained the steps for the mechanism. Since if it's a two-step mechanism, it will involve the formation of an intermediate, which is in this case is a carbocation intermediate, since nucleophilic substitution involves heterolytic fission, which is a process that involves the formation of an ion. On the other hand, a one-step mechanism will form a transition state, which I will elaborate more on as we proceed. The rate equations I have also stated here, which shows that this is a unimolecular rate determining step in which the halogenoalkane is reacting in the first step, and thus the overall order of the reaction would be 1. On the other hand, in an SN2 reaction, the rate equation is as follows, and the halogenoalkane and the nucleophile both appear in the rate determining step once, and thus the order of the halogenoalkane with respect to the reaction is 1, and the order of the nucleophile with respect to the reaction is 1, producing an overall order of reaction which is 2. This, as you can see here, the overall order of the reaction also agrees with the numbers stated in the name of these mechanisms, which is SN1 and SN2. On another note, SN1 reactions are non-stereospecific reactions, meaning they form 50% of each enantiomer equally, which I'll be covering in more detail as we proceed. While the SN2 is a stereospecific reaction producing one enantiomer of a compound. That's if a chiral carbon exists within the molecule. These mechanisms, when it's a non-stereospecific reaction, the mechanism does not need to be drawn in 3D or using stereochemical formulas. While if it's a stereospecific reaction, the mechanism must be drawn in 3D using stereochemical formulas. Polar aprotic solvents are used for SN1 mechanisms, while polar aprotic solvents are used for SN2 mechanisms, which I will also be discussing in part 4 of this series. Let's start. I prefer starting with SN2 mechanisms, as displayed below. A quick revision: SN2 mechanisms dominate in primary halogenoalkanes. They are stereospecific and thus are required to be drawn in 3D or using stereochemical formulas. It's a one-step mechanism that involves the formation of a transition state, not an intermediate. An example for an SN2 mechanism would be for a primary halogenoalkane, as chosen in part 1 of this series of videos. I chose chloroethane, in which the carbon atom, as seen here, bonded to the halogen, is bonded to one alkyl group, and thus it's primary halogenoalkane. The main reaction occurring would be the hydroxide ion displacing the chlorine atom to form ethanol plus the chloride ion. It's a simple substitution reaction. The mechanism, on the other hand, is not so simple. You should always state how many steps this reaction is, so it's a one-step mechanism. And this one step is the slow rate determining step of the mechanism. As you can see here, chloroethane has been drawn in 3D. A quick tip as to how to draw these molecules would be to locate the carbon bonded to the chlorine atom in this molecule. Always draw the leaving group, which is the halogen group, on this side, and drawing it in the plane of the paper, and draw a tetrahedral arrangement. Then plug in the rest of the groups bonded to the carbon atom bonded to the halogen in this compound, which would be 2 hydrogen atoms and the methyl group. The order of these atoms does not matter, but always draw the chlorine group on the left side or the halogen group on the left side to make things easier for you as we go. As you can see here, I've also denoted that the carbon atom has a partially positive charge, while the chlorine group has a partially negative charge, which attracts or seeks nucleophiles. In this reaction, the carbon atom bonded to the halogen group has low steric hindrance. Steric hindrance means crowding in terms of repulsive forces. This carbon atom is only bonded to 2 bulky groups, chlorine atom being a large group and the methyl group being a somewhat bulky group, but also 2 small hydrogen atoms. And thus, there's space in terms of crowding for the nucleophile to approach this partially positive carbon and donate its pair of electrons, as I stated here. This carbon atom with a partially positive charge bonded to the halogen has low steric hindrance because it's bonded to 2 small groups, 2 small hydrogen atoms, and thus can accommodate a 5th group, which in this case would be the nucleophile. Thus the repulsive forces are somewhat low, and the hydroxide ion can approach this carbon atom and donate its pair of electrons, which I have color-coded here in red. As the OH donates its pair of electrons to the partially positive carbon bonded to the halogen, the chlorine atom undergoes heterolytic fission and gains both these electrons and leaves as a chloride ions. It gains its own electron and the partially positive carbon's electron. In the process, this doesn't occur it's a one-step mechanism that involves the formation of a transition state. The transition state is a state with high activation energy, and this is why this part of the mechanism is considered the slow part of the mechanism, since it requires high activation energy to form this unstable transition state in which all species in the reactants are bonded together. This is the transition state in which indicates the process during which as the OH is forming, as the hydroxide ion is forming a bond with the carbon atom, the chlorine relieving group is leaving. So these dashed lines represent partial bonds in which all species in the reactants are bonded at that instant, which requires high activation energy and thus is slow. Once this transition state is formed, the reaction proceeds. The mechanism proceeds by the chlorine group gaining both electrons as stated previously and leaving the transition state, forming ethanol as drawn here, plus the chloride ion. One thing you should note is the nucleophile. Since the chlorine atom is a very bulky group and the methyl group is somewhat bulky, the approach of the nucleophile would be one-sided only. The nucleophile will always approach the carbon with a partially positive charge in a primary halogenoalkane from the opposite side of the leaving group due to steric hindrance. This would cause the inversion, which in this case there's no chiral carbon, but just for a means of explanation, the inversion of these bonds from the right-hand side to the left-hand side due to repulsive forces. These groups are repelled to the right here due to the large chlorine group on this side. But when an OH nucleophile, when a hydroxide nucleophile approaches this carbon and starts to form a bond, the repulsion from this side almost equals the repulsion from this side. Thus, these three bonds, the bond made by carbon with the methyl group and two hydrogen atoms, would form somewhat of a planar structure. The overall geometry of this transition state would be a trigonal bipyramidal geometry. If you were to connect these lines, you'd see that there's a pyramid on the right-hand side with a triangular base and a pyramid on the left-hand side with a triangular base. Once the chlorine atom leaves, the OH, the hydroxide group or the hydroxyl group, would repel these groups to the other side. Thus, there's an inversion of sides to which these bonds point, and the inversion is always one-sided since the approach of the nucleophile is also one-sided. Thus, if this were a secondary halogenoalkane in which a chiral carbon would exist, and this would be the chiral carbon, there would be an inversion of configuration in which only one enantiomer of the stereoisomers would be formed, which would be discussed later in other videos. As I've stated this here, inversion would occur if this were a chiral carbon, and the inversion is always one-sided since it's a one-sided approach of nucleophile. The nucleophile can only approach from this side and not from this side. So it approaches from the opposite side of the leaving group. The charge of the transition state is always the same as the charge of the nucleophile. If this were a neutral nucleophile, say ammonia, the charge of the transition state would be neutral. But in this case, this is a negatively charged nucleophile or ion. Thus, the transition state would have a negative charge, which I've also noted on this side. The charge of the transition state is always the same as that of the nucleophile, because you will be asked in exam as to what the charge of the transition state may be. I've also stated the rate equation for this reaction, in which the rate equals a rate constant multiplied by the halogenoalkane to the order of 1 with respect to the reaction, multiplied by the nucleophile to the order of 1 with respect to the reaction, as stated here, and the overall order of this reaction would be 2, as stated previously. Polar protic solvents favor this mechanism to occur because it causes some sort of stable, it affects the nucleophilicity of the nucleophile, which will be discussed in videos to come. Thus, quick notes to point out. This should be drawn using stereochemical formulas to indicate the inversion of these bonds from the right-hand side to the left-hand side. Always note the charge of the transition state, which is the same as the nucleophile. These curly arrows must always touch the pair of electrons that are being transferred, such as here and here, and indicate clearly to which atom they are being donated, as marks will be deducted if this was not the case. Thus, this covers SN2 mechanisms. I will be covering more examples in videos to come regarding a secondary halogenoalkane, which will clearly show the inversion in configuration and the formation of one enantiomer only, and in other videos that will cover the factors affecting the rate of the reaction, one of which is the choice of solvents. We always use polar aprotic solvents for SN2 mechanisms to favor the formation to favor this mechanism to occur. Thank you for watching.